Okay, in this video I'm going to talk about Van Aubel's theorem about cevians. And we need to specify here that it's about cevians because there is another theorem in plane geometry that is also called Van Aubel's theorem. So we need to differentiate. So basically we have a triangle and we have cevians in this triangle, which means segments connecting the vertices with points on the other sides or extensions of the other sides that intersect at a single point. So like this. And the theorem basically the theorem states how to express the ratio between this point where they will intersect and how it divides one of the cevians, to express it in terms of the ratio of the sides. So basically so let's denote this is A prime, B prime, C prime, and this is P. The intersection point is P. And so first, as a reminder, there is a Ceva's theorem, and because of this Ceva's theorem, the segments are called cevians. So Ceva's theorem, and it says that the ratio, so let's say B A prime over A prime C multiplied by C B prime over B prime A multiplied by AC prime over C prime B. This is equal to 1. So this is the Ceva's theorem, and now the Van Aubel's theorem. Van Aubel theorem says that we can express BP over PB prime. So the ratio in which the point P divides one of the cevians. So we can express this ratio in terms of the ratios on these sides. So this is equal to B A prime over A prime C plus BC prime over C prime A. Yeah, and all ratios are signed, so I put vectors here. It means that the ratio is either positive or negative, depending if these vectors point in the same direction or in the opposite direction. Yeah, and this theorem holds even if the point P is outside of the triangle. So if some of the points A prime, B prime, and C prime are on the extensions of the sides and not on the sides. Okay, so let's prove this. The proof is of the Van Aubel theorem, not of the Ceva's theorem. Ceva's theorem I'm going to remove it. Yeah, so the proof is going actually to use Menelaus theorem. So similar to the Ceva's theorem, there is also a Menelaus theorem. I'm going to formulate it now. So we have if we have a triangle have a triangle and we have a line that intersects the lines containing the sides. Then so A, B, C, and we have a line. So these 3 points on the sides and then extensions of the sides, they, instead of like in the Ceva's theorem, the segments connecting the vertices to these points intersect at some point. Here we have these 3 points simply lie on the same line, like they're collinear. So, and the criterion, so Menelaus theorem. Menelaus theorem says that A prime, B prime, C prime are collinear if and only if the ratios, so B, A prime, so the same ratio is in the Ceva's theorem, A prime C multiplied by C B prime over B prime A multiplied by AC prime over C prime B. So this ratios is equal to -1. So in this case, in this particular case, 1 point lies on the extension of the sides and 2 other on the sides. So we see that 2 of these ratios are positive and 1 of them is negative. So the product would be negative. But like in other cases, there, like some other would be positive and negative. But regardless, this always holds. So yeah, so this is a reminder, and we are so this is a separate. And so the proof now, the proof of the van Aubel's theorem. So for the, okay, let's draw the triangle again. So we have ABC, A prime, B prime, C prime. This is point P. So we are going to apply the Menelaus theorem to this triangle and this line. This triangle and this line. So so let's start with point B and go counterclockwise. So we have B C prime over C prime A multiplied by AC, because C is the intersection point, right, of this line, over CB prime multiplied by B prime P over PB. All of this is equal to -1. So this is the Menelaus theorem for this triangle filled with blue and this blue line. So now we we apply the Menelaus theorem to this triangle and this line. So we start with point B and now we go clockwise, not counterclockwise but clockwise. So we have B A prime over A prime C multiplied by CA over AB prime multiplied by B prime P over PB is equal to -1. So now Now we express from both of these equalities, we express the ratio that we need, like involving p. So basically no, we are going to express the ratios on the sides. So the ratios that we have here on the right hand side, this and this. So we have here, so the second ratio bc prime over c prime a, so this one. So this is expressed as bc prime over c prime a is equal to, so basically we move the other two ratios to the right hand side, so it's minus, and then we invert both of these ratios, so it's basically cb prime over ac multiplied by pb over b prime p. And here we express the ratio so ba prime over a prime c, so this one. So we express this ratio ba prime over a prime c is equal to minus, and then we invert both of these ratios, so it would be ab prime over ca multiplied by pb over b prime p, right? And now what we do, so we have here, in what we need to prove, we have the sum of these two ratios, so we sum these two equalities. So from this and from this, when we sum them together, what we get is so when we sum them together, we get b c prime over c prime a plus ba prime over a prime c is equal to, so is equal to the sum minus cb prime, I just rewrite everything, over ac multiplied by pb prime over b prime p plus, not plus but minus ab prime over ca multiplied by pb over b prime p. Okay, and so now we see that we have some common stuff here. So this is equal to, so we have b prime p and b prime p. Yeah, so the second, so you see that the second actually, the second ratio, so this whole ratio, this one and this one, this is just the same. So we can extract it. So we write p b over b prime p. And now here we have minus cb prime over ac minus ab prime over ca. So now we notice that ac and ca are almost the same. They are just the same they have the same magnitude but the opposite signs. So we can replace, so let's say we replace CA with minus, so CA is equal to minus AC basically. So then this minus and this minus, they cancel each other. So what we have is PB over B prime P multiplied by here minus CB prime over AC plus AB prime over AC, right? We replaced CA, vector CA, with minus AC. So now we have the same in the denominator. So then we simply have, so we have PB over B prime P multiplied by here the same denominator, and here we have minus CB prime plus AB prime. So now let's see what is CB prime and AB prime. So we have this here. So we have minus CB prime, so this vector, plus AB prime, plus this vector, right? So, well, we have, let's replace minus CB prime is the same as B prime C. So instead of minus CB prime, it's the same as B prime C, right? So this is equal to, I rewrite the first ratio, then we have here AC, and in here we have B prime C plus AB prime. So I replaced minus CB prime with B prime C. And now we have, so again, we have, well, it's better to start from AB prime. So we have A, then we have B prime, and then we have B prime C. So AB prime plus B prime C. So the sum of these two vectors, remember that they are on the same line. So the sum of these two vectors would be simply AC, the vector AC. And in the denominator we have AC. So they cancel each other. So this whole expression would be simply equal to PB prime over P prime P. And now we want to slightly rewrite it, because we need BP, we need to start from BP. So we invert basically both BP. Yeah, so we invert both of these vectors. So this is equal to minus BP over minus PB prime, and minuses cancel each other, so this is equal to BP over PB prime. And this is exactly what we need. So BP over PB prime, BP over PB prime, this is exactly what we need. So we started with this expression, so we started where we started. Yeah, so we started with this, with the expression on the right hand side here, and we ended with the expression on the left hand side. So started here and ended here. So this is exactly what we need to proof. So this concludes the proof. That's it for this video.